Hello, you all. This is Darrell Lee Berry Jr. back with some more linear algebra. Going to be doing some linear transformations on vector spaces. So we'll go ahead and get started. And basically, we're working on section 4.4. So chapter 4, section 4. And I'll be reading through this, preparing for the last exam and homeworks and such. And this is linear transformations on abstract vector spaces. Right, so this is what the game will be. And I may do more of writing on this one. And it's up to the book only when absolutely necessary. So it says in this section, we deal with linear transformations from R into Rm. And M equals not N. Or more generally, from one abstract vector space to another. So we start with definitions. It says let V and W be vector spaces. A function P, which goes from V to W, is called a linear transformation or a linear map if and only if a T U plus V equals T U plus T V for all U V in V, and B T C V equals C T V for all V that's in V and scalar C. So for a linear transformation, it's only, I think that's called distributive, and multiplicative with a scalar. So that's how it's different from, recall, a subspace has to be closed under zero, meaning it has to contain the zero vector, and W and V is in V. That means W plus V has to be in V. And for any scalar in V, CV must be in V. Shutouts for subspace. So it's not necessarily closed, like closed under some and closed under what have you, but it does follow two of the same components. And it says, of course, we can take the subspace V equals Rn, and W equals Rm. And all our previous examples will be appropriate as examples here, but the broad scope of linear algebra begins to become apparent when we consider vector spaces such as the set of all matrices or function spaces and consider maps between them. A very important example comes from differential calculus. So this is the first example. Any interval I, and it's a real interval. So we're going to define D when we're talking about differentiable functions. C1 I to C0 I by df equals f prime. That is, to each continuously differentiable function f, associate its derivative, which then is a continuous function. D satisfies the linearity properties by virtue of the rules of differentiation. So df plus g equals df plus dg, since f plus g prime equals f prime plus g prime, and d c f equals c df, since cf prime equals cf prime. So it follows the two linear transformation parameters. Although C1I is infinite dimensional, you can also think of restricting this linear transformation to smaller, possibly finite dimensional subspaces. For example, we can consider dpk through pk minus 1 for any positive integer k, since the derivative of a polynomial is a polynomial of one less degree. So it's saying that we could also do derivative is going to go some polynomial k to polynomial k minus 1, just like how x squared, the derivative is 2x. Here's example 2. It says here are some examples of linear transformations on abstract vector spaces. So A, it says the map M. So we have CO I to CO I given by MF T equals TF T. All right. So the map, okay. Seems like I can use more explanation, but we'll keep going. The map continuously differentiable, I imagine that is 0. And this is on an interval from 0 to 1 to C0. Also on an interval from 0 to 1 by T F T equals 0 T F S ds. So notice they're not explaining these, they're just like listing them. The map E, this is the map E. This is also on the interval, right? 2R3 by F equals F0, F1, F3. And the last one, D, the map P M, a 2 by 2, to M, 2 by 2, by transformation A equals B A, and B equals 1 2 1 1. We'll leave it to the reader to check that these are all linear transformations. So, as I said, it didn't seem like they was explaining much. It is also worth thinking about how one might restrict the domains and ranges to various subspaces. For instance, the subspaces of polynomials or polynomials of a certain degree. So it looks like the last part here is what determines the actual transformation. If we was to look at one of these. So let's take A and look at it. So it says M F F T equals T F T. So I can see how derivative of F equals F prime. Yeah. As we start to go farther into the book, I think they're getting worse at explaining stuff. Well, I mean, clearly here they even say they're not explaining it at all. Show you what I mean? Like, we'll leave it to the reader to check that these are linear transformations. It's like it's not even clear uh, what they're doing for this one. Like, is this, I'll say this is a derivative, but there's no prime on that. I mean, perhaps the integral is more clear. So in class, Professor went over an integral version. So I hate when when textbooks don't explain stuff properly or don't explain stuff at all like they're doing here. So it seems like sometimes these people just write books just to feel smart, like not to actually explain stuff. Let's look at this part here. So over here, this whole thing was expressed. So T F plus G T should equal integral 0 to T F plus G of S ds. So I guess maybe this would be F of S plus G of S ds. And we know that if we have that, we can split this up and say F of S ds plus 0 T G of S ds. And if we have T C F, T where C is any scalar, that would be 0 to T F S C ds. And we know that that's the same thing as 0 to T F S ds. So that's a linear transformation. So this one, it still seems, oh, hold up. So this is what I did here. So all we did was take this integral here, for the B one, and I extrapolated it with sum and the scalar. So this one is just saying EF equals that vector. So it seems like it would be a similar process. EFG, it'd be F of 0 plus G of 0, which is EF plus GF. And TA equals BA. So that would mean TA plus C would be BA plus CA. Excuse me, TA plus C equals BA plus CA. No, BA plus BC, which is the same thing as TA plus TC. So it looks like it works. These are I can make them out, but I still can't make out this one, but I'll keep going. It says just as the null space and column space are crucial tools to understand the linear map. So it says null space and column space crucial to understand linear map. And check my last video. I'll go over the four fundamental subspaces, so you definitely want to see that one. We define corresponding subspaces for arbitrary linear transformations. Okay, so let's do these. Definition. Let transformation V to W be a linear transformation so that's the kernel T that we went over in class today equals V that's in that subspace, that vector space, T V equals 0. So the kernel of T. So the kernel of T are all the vectors in the subspace V where the transformation of V equals 0. So like Professor was confirming today, this is essentially the null space of the vector space. The kernel of T are all the vectors that when you put them in a transformation, it equals 0. Because that's why they say the null space and the column space are crucial. And check the last video. But the null space is orthogonal to the column space. No, hold up. Null space is orthogonal to the row space. Null space is orthogonal to the row space. And the left null space is orthogonal to the column space. Because if we have a matrix, this would be, for instance, a vector that can that we can multiply times that uh, matrix, and it's going to equal 0. So the row space will have to multiply by that vector. So they're orthogonal because they equal 0. And that just leaves the left null space is orthogonal to the column space. They say the null space and the column space is crucial. So we'll keep going and see what they mean by that. And it also says image T equals all vectors W that's in subspace W such that W equals T V for some V in V. So all vectors W that's in the subspace W, every W equals a transformation of V. That's the image of T. So for every W that's in the subspace W, there has to be a V that can be transformed into that W for some V. We leave it to the reader to check in exercise 11 that the kernel of T is a subspace of V and that the image of T is a subspace of W. I mean, what it says that there, because we're all, as all vectors V and V, and all vectors W and W, so the kernel is before the transform and the image is after the transform. All right, so now we're on to example 3. This seems like a good place to stop, so I'll be back tomorrow, and I'll start with example 3 on page 226, and we'll keep working through till we get to some problems. So, like, share, subscribe. Help me get to 1,000 subscribers by December. Helping out with that, I appreciate it. And if you have any questions, put it in the comments, and I'll see you all tomorrow.